Hello, and welcome to Lesson 2 of Structures 2. In this group of lessons, we will be giving an overview of the many different types of loads on a structure, and we will also be looking at how to combine these loads in various load combinations as defined in the IBC. Today, we will also be focusing specifically on one group of loads known as gravity loads. Next week, we will be jumping into lateral loads. Finally, we will conclude our discussion for this second set of lessons with some calculation on tributary widths and areas. So, let's begin. What is a load? This might seem like a very basic question to you, but providing an exact answer and a precise definition can be a little tricky. I'm sure most of you probably already know what a load is, or you can at least provide examples of different types of loads, but it's important that we all have the same understanding of what exactly a load is. So let's see if we can find an exact definition of what a load is according to a structural engineer. And for that, we need to look at this document. This document is written by the American Society of Civil Engineers, and it's called the Minimum Design Loads for Buildings and Other Structures, and it's one of the reference standards in the IBC. And if we go to the definitions page of this document, we see that they do provide a definition for what a load is. And according to the American Society of Civil Engineers, loads are forces or other actions that result from the weight of all building materials, occupants and their possessions, environmental effects, differential movement, and restrained dimensional changes. So this definition is also pretty much just providing examples of what loads are, but regardless. This is the definition that we have for what a load is. So let's start to break this apart. First, we have the weight of all building materials. So that would include the walls, doors, windows, mechanical equipment, lights, plumbing. Even the structure itself has weight, and structural engineers need to design for all of that. Next, we have occupants and their possessions. Occupants, of course, means people in the building, and possessions are anything that they bring along with them. Next, we have environmental effects. And of course, up here in the Northeast, the first thing we probably think about when it comes to environmental effects is snow or rain. Water is actually quite heavy, about 62.4 pounds per cubic foot in density. So if we have a lot of snow or rain up on a roof, we're going to need a structure that can support that load. All of these loads that we've discussed up until this point have to do with weight due to gravity. If there were no gravity, none of these objects would have weight, and there would be no load imposed on the structure. And so we'll call these gravity loads. But of course, there are also environmental effects that don't relate directly to gravity. For example, wind loads are caused by changes in fluid pressure, and when that pressure hits the side of the building or pulls on other parts of the building, that creates a load. Earthquakes also create loads on a structure, but earthquakes are fundamentally very different from wind loads, and we'll talk about that more next week. Soil pressure on a retaining wall, or hydrostatic load, is another environmental effect on a structure. These loads all push and pull on the building horizontally, and so we'll call them lateral loads. And again, we'll talk more about these lateral loads next week. Now let's talk briefly about these last two categories: differential movement and restrained dimensional changes. Well, differential movement is primarily referring to the foundation. If you have a building, a long building like this, on level ground, and let's say that the soil on this side of the building is much stiffer than the soil on this side of the building. And so this side of the building may only settle an inch, while the right side of the building may settle much more. And so that's going to cause stresses in the structure of the building. Lastly, we have restrained dimensional changes. What they're referring to here is thermal expansion and contraction. If a brick veneer, for example, is in direct sunlight all day, it's going to heat up to a very high temperature, and it's going to want to expand. Then, later at night, as the brick cools, it's going to shrink. If there are enough control joints along that veneer wall, the brick can expand and contract freely. But if the dimensions of the wall are restrained, then there will be stresses that develop inside the brick and potentially cracking. So now let's continue to look through this document and look through what the definitions of each of these different types of loads are. And we'll start with chapter 3, which is dead loads, soil loads, and hydrostatic pressure. And we can see here the definition for dead loads states that dead loads consist of the weight of all materials of construction incorporated into the building, and they provide examples. The main point here is that dead loads are permanent loads. So mainly that's talking about the structural components. And so if we have a wall in the building that is an architectural partition and is not part of the structural system, then that would not be considered a dead load. Mechanical equipment can be a little bit of a gray area, and I've actually heard arguments for both sides. But in general, most mechanical equipment is not going to move during the lifespan of the building, and so most structural engineers consider mechanical equipment to be dead load. And the justification for that in the code would be this statement right here, fixed service equipment. Soil loads and hydrostatic pressure we are going to save toward the end of the course for when we talk about concrete and foundations. Now I'd like to point out that this chapter, chapter 3, is relatively short. And that's because due to their nature of being permanent loads, these loads are static. In other words, if we plot on a graph with time on the x-axis and the force, the magnitude of the force in the y-axis, that line is going to be perfectly flat. So we know that the load is not going to change ever during the lifespan of the building. We can also calculate these dead loads very easily because we know the weights of all of the materials. We know how much steel weighs, we know how much concrete weighs, etc. And so there isn't really much guesswork or need for too much research when it comes to dead loads. But as we'll see as we continue onward, that's not true of all of the loads that we will be talking about. The next type of load we're going to be talking about are live loads. And to refer back to the definition, this is where we talked about occupants and their possessions. Occupants, of course, includes the owner, and the owner's possessions can include chairs, desks, tables, other pieces of furniture, art installations, what have you. All of that would be live load. Anything the owner might pick up and move around or replace, all of that is considered live load. And here the exact definition of a live load is stated as a load produced by the use and occupancy of the building or other structure that does not include construction or environmental loads. So basically, they're defining live load as anything that's not any of the other loads. Like I said before, everything in structural engineering is very cyclical and interlinked, and it can be hard to know where to start exactly to define things. But nevertheless, a live load is essentially anything that can be found inside the building that has weight that is not permanent to the structure. Now, when we talked about dead loads, I mentioned that dead loads are basically static loads. They don't ever change. And as you can imagine, based on our discussion of live loads so far, if I draw just a basic elevation of a building like this, and I draw just a little person here. So that person, the weight of this person is considered live load. And this person, of course, is not going to stay in one spot for their entire life, for their entire existence. They're going to move around. So the load on this member is going to change. And so this is clearly not a static load, and instead it's a dynamic load, meaning that the load changes over time. But of course, the structural engineer is not going to sit down and analyze every single moment in time throughout the entire lifespan of a building. Instead, they're going to look for the worst case scenario and consider that brief moment in time where a member is experiencing its worst case stress and design for that load. And so structural engineers take what is a dynamic load and turn it into a worst case scenario static load, a worst case single instant in time, and design for that. And if you design the member for that single worst case instant in time, then of course the member will be adequate for all other moments in time. And it's important to note that the worst case moment in time may not be the same for every member in the building. So, for example, one might assume that the single worst case moment in time might be for when the building is completely full. But in fact, if we were to draw a cantilever out here, and if we were to design that cantilever for the maximum possible occupancy that we're expecting over the lifespan of the building, both in this room and in the room behind, you can see that this arrangement would not be the worst case scenario for this cantilever, because of course we're placing more weight on the backspan, which is helping that cantilever. So actually for this cantilever, the worst case scenario would be when we have full live loading on the cantilevered member and no live load in the adjacent space. So each component has a different worst case scenario in time, but we're designing each of them according to one specific instant, or one quote-unquote static load condition. And so we call this method of analysis pattern live loading. And basically, we're just putting different live loads in different locations throughout the building and picking the worst possible arrangement of those live loads for each component. Next, we have flood loads, so we're getting into our environmental loads here. And note that not every building is going to be designed for flood loads. According to this general section here, the provisions of this section apply to buildings and other structures located in areas prone to flooding, as defined on a hazard map. And so for this course, we won't be focusing very much on flood loads. Next, we have snow loads. And snow, again, is somewhat dynamic in that it will build up over time and it may shift around on the roof. However, we're only going to look for that single worst case scenario for when we design the members on the roof. And so we're going to take a dynamic load and analyze it as a static condition. Next is rain loads. And the one thing I want to point out here is this ponding instability. And ponding refers to the retention of water due solely to the deflection of relatively flat roofs. So it's actually easier to think about this when you see pictures of it. But you can imagine that as it rains, the water is going to add load to the roof due to its weight, and that's going to cause the roof to deflect. And as the roof deflects, more rain and more water is now going to collect in that dip that's caused by the deflection of the initial rain load. And so as it deflects, more load collects, and then it deflects more, and then gathers more load, etc., etc. And sometimes this can lead to collapse. And lastly, in our group of gravity loads, we have ice loads. Again, ice loads are not something that we typically include in design, although if you are designing somewhere up in Alaska, then you'll definitely need to consider ice loads. And so you can see we're less than a sixth of the way through this document, and we've already covered all of the gravity loads, which means that the rest of the document is all of our lateral loads. And just so you can see here, all of our gravity loads were covered in the first 100 pages of this document. The remaining 558 pages are all going to cover just two more loads, seismic and wind. And so we'll be looking more at lateral loads and the remaining 558 pages of this document next week. Don't worry, we definitely aren't going to look at every single page. We're just going to pick out the ones that are most relevant for you to know as an architect.